Thanks. I'd like to thank you for having us here to present the results from this novel study. I express gratitude for my collaborators, for which this project would not have been remotely possible. The subtitle of this project name can only be the A-Team. So please email me if you want the slide deck, as there are too many details to discuss completely. GeoClaw and sea level rise. So GeoClaw uses a single line to incorporate sea level rise into the modeling. And we applied a suite of average return period tsunami at 4 sea level states, 0, 1/2, 1, and 2 meters. And we did this for 6 average return periods. And we applied these 24 models at 7 locations for 168 tsunami model runs. We'd initially planned on using GeoClaw for our tsunami modeling, and I wrote the code for all of these models, but due to unforeseen circumstances, we used Pat Lynette's Solaris tool. The Solaris tool addresses sea level rise in the same manner, a static change in initial water levels using the same topobathy data. So I thought it'd be useful just to walk us through the project, even though we didn't end up using GeoClaw. I updated the slide deck this morning. Since AMR ratios were discussed earlier, I threw in the slide to show what ratios we were going to use with our GeoClaw model. So we conducted a series of analyses to evaluate the influence of sea level rise on tsunami hazards in California. We did this for 7 regions shown on the map. First, we conducted tsunami modeling for a range of return periods and sea level states. We used the output from these models as input for the following tasks. We conducted risk and vulnerability assessments to estimate the change and risk to people along the coast, and we included an analysis of culturally important structures. We applied tsunami engineering, coastal erosion, and sediment transport analyses to estimate how much the shape of the seafloor will change and how much damage might be inflicted upon maritime infrastructure. We calculated the tsunami design loads on hypothetical structures as outlined by the American Society of Civil Engineers and adopted into the California Building Code. And then we also performed structural reliability analyses in these locations using wood frame structures. And let's go through these tasks and take a look at some of the results. So hold on to your hats, everyone. For task 3, we conducted tsunami modeling for the 100, 200, 475, 975, 2475, and 3,000 year average return periods, or ARPs. And to avoid being tied to any particular sea level rise projection or forecast, which seemed to change on an hourly basis, we adopted to use a range of sea level states to bracket our results. And I mentioned those sea level states. For most of this presentation, we'll include examples from Crescent City, but each region has a different landscape that affects how tsunamis may inundate those landscapes. So here's from Crescent City, California. This map shows tsunami inundation as filled polygons. Lighter blue represents the 0 meter, and darker blue represents the 2 meter sea level states. From upper left to lower right, we have increasing average return periods. The key table is the lower one that shows the increase in onshore inundation area as a percentage. Obviously, there's too much information to consume on this slide. And then we also showed how inundation extent compares to population density in all of our locations. This is in Crescent City that has a lower population density compared to other regions like Alameda, Santa Cruz, and San Diego. There are a few places, so this is Humboldt Bay in Northern California. There are a few places where the sea level state significantly increases tsunami inundation area. This may be because the 0 meter sea level state already inundates the low-lying, low-relief areas around the bay, and the onshore boundary of tsunami inundation is controlled by elevation increases. For example, the northwestern part of Eureka is bordered by an ancient sea cliff, and the coastal stream valleys are bound by similarly steep cliffs. These cliffs prevent inland penetration of tsunami waves. Just like in Eureka, this is in Alameda, the east part of San Francisco Bay. Just like in Eureka, where there is a sea cliff along the boundary of Humboldt Bay that controls tsunami inundation for all ARPs, there appears to be a similar elevation topographic boundary in the Richmond area. Note the northwest trending boundary of the tsunami inundation along the southwestern part of Richmond, and there's also a north-south trending boundary of tsunami inundation just north of the eastern part of Richmond Yard. This is in Half Moon Bay or Pillar Point, just south of San Francisco. For all ARPs, sea level state has a modest control for tsunami inundation area. This may be partly due to the presence of an ancient sea cliff along the coast east of Pillar Point Harbor and Half Moon Bay. The low relief of the coastal plain where the Half Moon Bay Airport is located may contribute to the significant tsunami inundation here. This area is one of the few places that were inundated by the 1946 tsunami sourced from the Alaska Aleutian subduction zone. Here we're in Santa Cruz, just further south. The sea level state controls for tsunami inundation extent are limited in the Santa Cruz, likely due to the sea cliffs along the coast of most of Santa Cruz, except for places along river and coastal stream valleys. These river and stream valleys are the places where the sea level state influence is most notable, such as along the lower San Lorenzo River in the western part of the map. Here, now we're in Southern California in Ventura. As for Santa Cruz, there's an ancient sea cliff along the trend of the highway along southern Ventura. The 475, 975, and 2475 ARP 2-meter sea level rise state tsunami models all terminate at the sea cliff. Also, like in Santa Cruz, the Ventura River Valley in the western part of the map is a place where the sea cliff has been eroded, so that does not serve as a barrier for tsunami inundation there. Here we are in Los Angeles, the ports of Los Angeles and Long Beach in Southern California. The northern part of the region shown here shows tsunami inundation controlled by the natural topography that has low relief, increasing in elevation with distance from the coastline. The southern part of the region shows tsunami inundation controlled by anthropogenically modified topography. The piers serve as barriers to tsunami inundation, but once the pier elevation is exceeded by tsunami size or sea level state, the pier is easily inundated. And then the last place in San Diego, Southern California, the topography in the region of San Diego is similar to that of the Richmond and Alameda area. There are regions of higher topography, like east and west of the airport, Point Loma, and the Mission Hills, that border areas of lower-lying, low-relief topography, like the airport and the region between the Naval Air Station North Island and Coronado. There's also an ancient sea cliff along the southwestern part of San Diego. The 2-meter sea level state tsunami models take advantage of these low-lying areas and are impeded by the sea cliffs and areas of higher topography. For Task 4, we conducted risk and vulnerability assessments. And it was really exciting that our partners at NIAM IT, who are FEMA contractors, developed an open source software called Sphere to run the tsunami risk analysis HAZUS outside of Esri, where each run took only a few seconds. For now, casualty analysis still needs to be done within ArcGIS Pro, but they're working on that. They helped to conduct both loss and casualty estimates. And we also ran vulnerability assessments using Esri Business Analyst. And finally, we evaluated the changes in tsunami flow depth for culturally important structures. These 6 plots show the standard HAZUS losses in US dollars for all ARPs in sea level states, and this is for Crescent City. And I'm just showing these plots just to show you, what we did. There's not really time to consume them completely. These plots show total casualties versus sea level state for the Crescent City area. Day is plotted as lighter blue and night is plotted as darker blue, and preparedness level controls the outcomes. Oops, sorry. There are more casualties at night and fewer casualties for those that are good prepared. Tabular summaries of our assessment of demographic and socioeconomic characteristics for at-risk populations include breakdowns of key vulnerability factors such as age distribution, economic indicators, transportation, and disability-related access issues, language barriers, and business and employment impacts. This plot illustrates how total exposure changes as sea level rises for the resident population on the left and the daytime population on the right. The Del Norte County Built Environment Resource Directory database, managed by the State Office of Historic Preservation, includes 54 structures that are located within the footprints of all tsunami models here. The mean and standard deviation of the flow depths for all structures are plotted at the right, sorted by return period, top to bottom. There is very little impact to these structures from the 100 and 475-year models. The mean flow depths for the 975-year ARP is low, but exceeds 2 meters for the 2-meter sea level state, and the mean flow depths for 2475 model mostly exceeds 2 meters. For task 5, we applied sediment transport models to estimate areas of deposition and erosion, and we also used current velocities to calculate current-driven damage in harbors. Here are the results of the sediment transport modeling at Crescent City for 4 return periods and sea level state from top left to bottom right. These maps show the common sedimentation and erosion patterns in the Crescent City harbor area. Within the harbor and boat basin, we see sedimentation in blue. Around the mouth of the harbor, erosion is shown in red, and these types of patterns are found at all locations statewide. In harbor improvement reports produced by the CGS and PatLinet, we use fragility analysis at harbors and marinas to identify weak parts of existing maritime infrastructure. During this analysis, we apply force loads to maritime infrastructure based on the physical shape and size of docks and the condition of connecting devices like cleats and pile guides shown in these photos. Data from infrastructure surveys conducted at each marina serve as constraints for this analysis, and the condition of cleats and pile guides are key points of failures that we consider. This failure map for Crescent City Harbor shows the chance of cleat failure for the 2475 ARP for all sea level states. Higher damage is in red. Failure chance is highly non-uniform in space and does not change significantly with sea level rise. This is because damage is related to velocity, which does not change appreciably with sea level rise. There were a couple statewide results that we present, and this is one. This plot shows the statewide average failure chance on the vertical axis for cleats on the left and pile guides on the right for increasing return period top to bottom. So it goes from 100 years at the top to 2475 years at the bottom. The black line represents the mean, and the red dashed lines represent the standard deviation. In most cases, the mean changes little or zero with sea level rise, particularly at the higher sea level states. Some sites have increased risk of damage at higher sea level, while other sites have decreased risk of damage. And this reinforces a finding from several of these analyses that site-specific analyses need to be conducted to evaluate the impact to maritime infrastructure. For task 6, we calculated ASCE tsunami design loads for hypothetical structures, and we conducted structural reliability analysis. And I'm going to skip through these slides to save some time. And so in summary, here are some of the highlights. Changes in tsunami hazard as influenced by sea level rise vary statewide. Even modest increments of sea level rise significantly escalate potential structure damage. At higher ARPs, total losses reach billions of dollars. Casualty totals significantly increase with longer ARPs. For example, in Humboldt County, daytime casualties more than doubled with sea levels rose from 0 to 2 meters for the 2475 model. River and stream channels and entrances to bays and harbors all show erosion, and channels within bays and harbors show sedimentation, which will be important for post-tsunami recovery. The change in failure chance at maritime facilities due to sea level rise is irregular and relatively minor. In some cases, sea level rise increases the average chance of failure for that structure. In other cases, it decreases. And lastly, in general, in an average sense, it is reasonable to expect that structural loads increase with increasing sea level. However, due to site-specific effects, such trends are not guaranteed. And using probabilistic structural reliability analysis of unreinforced wood frame buildings exposed to tsunami inundation along California coast, we show that tsunami depths escalate non-linearly with rising seas. So I'd like to thank you for having us here today. I'll stop sharing.